Of the three possible responses to an applied load, we're most interested in equilibrium. So for now, let's go even further in restricting our attention to only looking at particles. So we're going to look at particle equilibrium. Remember, the difference between a particle and a rigid body is that particles can't experience moments. They don't have any extent, and so forces can't be applied at a distance to cause a torque. The basic idea for a particle is that if a particle system is going to remain in equilibrium, all of the forces acting on it, sum of forces, have to equal 0. There are two types of forces that act on particles. We have the applied forces, which are what we're doing to the system. They're what we think of when we see the problem. So any external load and weight. Weight's one that we often overlook. So external loads and weight. In addition to that, we also have reaction forces. This goes back to Newton's laws. And these are usually unseen. They're the things that act to oppose the applied forces and keep our system in equilibrium. And we usually have to think about them a little bit because they don't necessarily show up in the problem statement and things like that. Reaction forces typically act at the location that the system attaches to the rest of the world. So it's places like mounts and supports. For a particle, this tends to look like forces in things like ropes and cables and normal forces from surfaces. Normal forces. So two systems that we could look at real quick here. Maybe one is a particle that is suspended by a couple of cables that are attached to some walls or whatever. Here we have some cables or some ropes, and those would be the reaction forces. Another one might be a particle that is sitting in some sort of a V groove. So a thing like this, where we've got a wall here and maybe some other wall like that. And the normal forces from those walls are the reaction forces that are going to hold this thing in place. So the first step to solving a particle equilibrium problem, step 1, is the same step as to solve any static system. It's to draw your free body diagram. And remember, we want to establish a coordinate system. We want to draw our object, and we will then put the loads that are acting on it. So we have the weight, which I'll call W, and we have the cable tensions, which I'll call T1 and T2, like so. T1, T2. You'll see we have assumed directions for those. And I've colored them differently to indicate that these are the reaction forces. So what I did here was I started by drawing all the applied loads and then added the obvious reaction forces, things like cables, ropes, surface normals. And what I want to make sure of is that I see at least one reaction force component in each direction that could oppose an applied load. If we didn't have anything in the horizontal direction here, say at T2, we'd have a problem, which is that this thing wouldn't necessarily be in equilibrium, and so we'd have to spend a little bit more time thinking about the problem. Once you've got your complete free body diagram, the second step is to go ahead and write the force balances. And we're going to do that in each coordinate direction. So for this problem here, that means we're going to write a sum of forces in the x direction, which is going to look like minus T1x, because the horizontal component of T1 is acting to the left, that's the negative x direction, plus T2, and that has to equal 0 if this is in equilibrium. And we'll do sum of forces in the y direction, which has a minus w because the weight acts down, and a positive T1 y because the y component of T1 acts upward in the positive y direction. The third step in solving any of these problems is to work out any geometry that you might need. Geometry. So, for example, this T1 here acts at some angle theta. Let's pretend like we know that. Now we can use trig and we can start solving things. So, for example, in trig, we know that the cosine of an angle is equal to the opposite over the adjacent over the hypotenuse, which in this case would be T1x divided by T1. And so we can solve that and find that T1x is equal to T1 cosine theta. And we know that sine theta is equal to T1y over T1, opposite over hypotenuse. We can solve that for T1y, which gives us T1 sine theta. We can sub those now into our force balances and discover a minus T1 cosine theta plus T2 equals 0 and a minus W plus T1 sine theta equals 0. And it's at this point that I like to do an audit to make sure that the number of equations, in this case 2 equations, matches the number of unknowns. So for example, T1 and T2 could be our unknowns in this problem. If we didn't have the same number of equations as unknowns, we couldn't solve this, and so we'd have to go hunting. Maybe we're missing an equation or a geometry relationship that could eliminate. Right here we had T1x and y, those are unknowns, and we eliminated, this went from 2 to 1 number by becoming T1 multiplied by a known geometry constraint. Or maybe we've identified too many reaction forces and we've actually created what would be called a statically indeterminate system. Either way, we'd have to go hunting for more equations. In this case, we're good to go, so we get to move on to the final step. Whoop, give away the bottom of my screen here. The fourth step, which we're not actually going to do here because we don't know what the question's asking, is to simply solve the algebra. 2 equations, 2 unknowns. This is a solved problem. It just depends on what the problem statement gives us and what we're looking for. Depending on the question, we could have been looking for T1 or T2. We could have been looking for the W. What's the maximum weight that this cable system could hold? Or we could have been looking for theta. What angle for T1 gives us the balance that we're looking for given some other constraint? Regardless, these 4 steps always work out. So sometimes we might not know a reaction force, other times we might not know a limit for an applied load. Either way, if you follow these 4 steps to set up your solution, you'll never find yourself getting stuck.